Today's lecture is a continuation from yesterday, but actually it's quite a different topic for today. And I want to talk about the symmetrized bidisc, which is denoted by gamma, and gamma contractions. So gamma is just defined to be the set Z plus W, ZW, Z and W being complex numbers of modulus less than or equal to 1. So that's a subset of C2, of course. And it's nice to have a mental picture of any set one's interested in. Of course, there are 4 real dimensions in C2, and so you can't draw it on a 2-dimensional blackboard, but you can draw gamma intersection R2, and that is a triangle. It's an isosceles triangle, well, with its interior. So it looks convex if you just see its intersection with R2, but if your eyesight is so good that you can see into the imaginary dimensions as well, then you would see that it's not convex. So here are some properties of gamma. It's not convex. So for example, you can see if you put Z and W equal to 1, you get the point 2, 1. And if you put Z and W equal to I, then you get the point 2i, minus 1. And if you take the midpoint of those two, you get the point 1 plus I, 0. And that is clearly not of this form, because if ZW is 0, then one of them's got to be either Z or W has to be 0, and the other one would have to be 1 plus I, which does not have modulus S equal to 1. So that is not in gamma. It's not circled. So in other words, if you've got a point in gamma and you multiply both components by the same complex number of unit modulus, you don't necessarily get something in gamma. So 2, 1 is in gamma, but minus 2, minus 1 is not in gamma. It is star-like about the origin. So it's immediate from the definition that if you take a point in gamma, so if Z and W are both in the closed unit disk, and you multiply by some number R between 0 and 1, then you would get, so if, suppose you've got SP in gamma, and 0 less than or equal to R less than or equal to 1, then it's obvious that RS, R squared P is in gamma. So it's got that kind of homogeneity. But what's not at all obvious is that you can rub out that 2 there and that it will still be true. So that's just an entertaining exercise. It is polynomially convex, And another interesting property that it has, which is of some significance in what I'm going to talk about, is that its distinguished boundary has some non-trivial topology. So the distinguished boundary or if you like, the Shilov boundary of the algebra of functions which are continuous on gamma and analytic in the interior so it's what you would think. It's just that you take mod z, it's point z plus w, zw, where mod z equals 1 equals mod w. And this set, if you think about it, is actually a Möbius band. So it has an edge. That's very different from the bidisc. The natural set that you would compare it with is the bidisc. The distinguished boundary of the bidisc is the 2 torus, which is a manifold. But this one, it's a Möbius band, so it itself has a boundary. And that plays a role in some of the function theory of this set gamma. Now, when we're doing function theory on gamma, we want, you can use these z and w coordinates sometimes, but it's also convenient to have a description in terms of these variables, the sum and the product. So I use little s and little p, standing for sum and product, to deal with, to indicate these 2 components here. And it's useful to have the characterization in terms of the sp coordinates. So here's a characterization, some characterizations of gamma. So for a point SP and C2, S comma P belongs to this set gamma if and only if mod S is less than or equal to 2 and mod S minus S bar P is less than or equal to 1 minus mod P squared. Now, where does that come from? Well, there's an old result of Isai Schur from, I think, about 1911, which tells you if you have a polynomial of any degree, it gives you a way of ascertaining whether the zeros of that polynomial lie in the unit disk, just in terms of the coefficients. You don't actually have to solve the equation. And so SP in gamma, that's the same as saying that the roots of the equation, let's say z squared minus sz plus p, lie in the closed unit disk D. And so you can apply Schur's result to this, and you find that this is exactly how it works out. So that's a useful criterion for a point to belong to gamma. And another one is the following: twice mod S minus S bar P plus mod S squared minus 4P plus mod S squared is less than or equal to 4. So if you get bored later on, I invite you to try and prove the equivalence of these 2 entirely elementary statements, just statements about these pairs of complex numbers, those two things are equivalent. So far I haven't given you any reason why we should be interested in this set gamma and what on earth it's got to do with pairs of commuting contractions. So as I said yesterday, all this is building up to a model theory, operator model, functional models for pairs of commuting contractions. So let me just go back a few years. So everything in this lecture is joint work with Jim Agler of the University of California, San Diego. And we started around 1999 studying the function theory of gamma in connection with a problem that arises in control theory. We wanted to try and solve a version of the Nevinland-Pick problem in which you're looking for functions which are analytic in the disk, but with values not in the disk, but in gamma. And that connects with what's called the spectral Nevinland-Pick problem. So we wrote our first paper about 99 on that. And then we discovered that there's actually a very rich function theory, quite beautiful function theory of the set gamma. And so then we started thinking about the associated operator theory. And so we wrote a paper in 2003 in the Journal of Operator Theory called a model theory for gamma contractions. And so what I'm going to tell you about is mostly what's in that paper. So this is not very new, and I haven't actually worked on the operator theory associated with the gamma since about that time. But in tomorrow's lecture I want to tell you about some recent developments due to various Indian mathematicians, particularly Tirtha Bhattacharya, who have recently developed the Noddy-Foyash model for what we call gamma contractions, which I will define shortly. So here's something something elementary again. So if you have a complex number of unit modulus, alpha, and z, w, any old complex numbers, and if you put s equals z plus w and p equals z times w, and you look at this quantity, 2 minus alpha s squared minus 2 alpha p minus s squared. That turns out to be 1 minus mod z squared times times the modulus of 1 minus alpha w squared plus 1 minus mod w squared times the modulus of 1 minus alpha z squared. So you can just expand them out, and with any luck they will come to the same thing. So this tells us something quite interesting. See, if we come back to these characterizations up here, these are very hard to deal with when you're trying to do function theory, because you've got all these modulus signs and complex conjugate signs in there. And so you're trying to construct a function from the disk into gamma. That means you've got to construct a pair of functions s and p from complex valued functions s and p on the disk, such that these inequalities hold pointwise. And of course, these are very hard to analyze. But from this identity here, you can get a much more amenable kind of condition for a point to belong to gamma. So if you stare at this and think, if z and w are in the closed unit disk, then everything on the right-hand side is positive, or non-negative. And so this would have to be non-negative for any pair s comma any pair point s comma p in gamma. And so you get modulus of 2 alpha p minus s over 2 minus alpha s is less than or equal to 1 for all s comma p in gamma, and alpha, well, initially I took alpha to be on the unit circle, but actually you can see this is a rational function. It's analytic in alpha, and so it would hold for alpha in the whole of the closed unit disk. That's actually not quite precise, because this thing would have a singularity at the point SP not equal to. There is just one point in gamma where this fails to be defined, and that's the point 2 alpha bar squared if mod alpha equals 1. And this plays such an important role, this function here, that I'm going to call it, give it a name. So let's define phi alpha of s comma p to be this quantity, 2 alpha p minus s over 2 minus alpha s. And I've observed, as long as you believe with my identity there, I've shown that phi sub alpha maps gamma into the unit circle, the closed unit disk rather. And actually there's a converse. So for SP and C2, we have, this is yet another characterization. Maybe I should write it up here as well. Here, this is mod phi alpha of s comma p is less than or equal to 1 for all alpha in the disk. And the thing is that this is an analytic condition for s comma p to belong to gamma. And that proves to be a very useful feature of it. So that's the set gamma. Now I have to try and persuade you that it's relevant.
I'm sorry, may I ask a question? Is it obvious or not that converse is true, that it's not only in one direction but in opposite one? because that if this is less than 1, then we have some positive number, but why it could be represented in
yes.
this form? It's not obvious. It's like
Let's see, how does one prove that?
If it requires some thinking or some arguments,
yes.
But
I'm certain it's true, but to think exactly how...
Is it evident or not? Because it's not...
It's not completely obvious to me at the moment, I have to say. Now, presumably, so you ought to be able to get it from this identity. So if mod z, say you have a point which is not in gamma, then you write it as z plus w, comma zw for some z and w. The fact that it's not in gamma means that either z or w has modulus greater than 1. So say z has modulus greater than 1. Now this is negative. If mod w is greater than 1 as well, then of course that's the sum of two negatives, and so that would be prove it. But if mod z is greater than 1 and mod w is less than 1, I guess you would have to fiddle around to show that you could choose an alpha that made this one bigger than this one. I hope something like that would work. That's not how it was proved in our paper, but it ought to be possible to do it that way, I would think. Right, so let's come on to commuting pairs of contractions, or pairs of... Does one say commuting pairs or pairs of commuting? I don't know. So, commuting pairs of contractions. So let A and B be contractions on a Hilbert space H. I always assumed Hilbert spaces are separable, and AB equals BA. Then there is a celebrated and remarkable theorem of Ando that says that there is that the pair AB have a commuting unitary dilation, a commuting pair of unitary dilations. So let me just explain what that means. There exists a Hilbert space K, which contains H, and commuting unitaries U and V on K such that with respect to a suitable orthogonal decomposition of K, U can be written by an operator matrix like this. It's going to have A in the middle, and it's going to have 0. So it's a upper triangular matrix. And V likewise only for B. So you've got and that's with respect to some orthogonal decomposition of K, of course, but it's the same orthogonal decomposition for U and V. That's the important part. So it's something direct sum H direct sum something. So there are some subspaces of K So when you write K as this orthogonal decomposition, U and V have matrices of this form. And so this implies that if you take for any polynomial in two variables, any polynomial G, if you take G of AB, that is the compression of G of UV to H. And therefore you can get, so there's Andrews inequality, which is a immediate consequence, that the norm of G of AB is less than or equal to the sup of modulus of G on, well, certainly on the joint spectrum of the pair, commuting pair UV, but that is contained in the bidisc rather. So this is the sup of mod G on the bidisc. And now a consequence of this observation, it's more than an observation, consequence of this major theorem it tells us something about the symmetrization of the operators A and B. So A and B are commuting contractions, and we can consider the operators S equals A plus B and P equals AB. So these are commuting operators on H. And so for any polynomial G, I want to look at the norm of G of SP. So let me draw a little picture here. Here's the bidisc. Here's gamma. Here's the map pi, defined by pi ZW is Z plus W ZW. And I'm going to consider a polynomial G, say onto the disk. And F could be G circle pi. Let's look at G of S, the norm of G of SP. Well, that S comma P is pi applied to A comma B. So that's G circle pi of A comma B. So that's F of AB. F is a polynomial. But now we've just seen from Andrews' theorem that that's bounded by the sup of mod F over the bidisc. So that's the sup over the bidisc of the modulus of G circle pi. And so that's clearly the same as the sup over gamma of mod g. So for any polynomial g in two variables, if you form the operator g of s comma p, then its norm is at most the sup of mod g on gamma. And that's sometimes expressed by saying that gamma is a spectral set. For s comma p. And that's such a nice property that it deserves a name. And so we'll say, we'll make a definition for a commuting pair of operators S and P S comma P is a gamma contraction if it has this property that we've just described. If for all polynomials g, the norm of GSP is less than or equal to the sup over gamma of mod g. So that's the notion of gamma contraction, which is going to be central to this and tomorrow's lecture. It's a commuting pair of operators for which gamma is a spectral set. And we've just seen that if A and B are contractions which commute, then their symmetrization, A plus B, AB, is a gamma contraction. As follows from Ando's theorem, as I indicated. But it's good to have some other examples. So here are some examples of gamma contractions. So there's this one that we've just seen, but they're not all of that type, otherwise it wouldn't be so interesting. So what about 0 comma p? Take the first component to be 0, then it's easy to see that that will be a gamma contraction if and only if p is a contraction. Instead of taking S to be 0, you could take P to be 0, so you could look at an operator, a pair of the form S comma 0, and it turns out that this is a gamma contraction if and only if the numerical radius of S is less than or equal to 1. So the numerical radius of S is defined to be the sup of over norm x less than or equal to 1 of the modulus of Sx inner product x. Now, how can we be sure which operators, which gamma contractions are of the form A plus B? AB. Well, if S comma P is equal to A plus B, AB, then of course S squared minus 4P will be A minus B squared. And so that says that S squared minus 4P has a square root. And not only that, but that square root actually commutes with S and P. So if SP has the form like that, then S squared minus 4P has a square root that commutes with S and P. And so if we come back to this example here, 0 comma P is a gamma contraction. But it's easy enough to find a contraction P that doesn't have a square root at all, never mind one, well, yeah. So if P is a contraction that doesn't have a square root, then 0 comma P is an example of a gamma contraction that is not the symmetrization of a pair of contractions. But that's a slightly boring example, so let me give a more interesting one. If you look at so on H2, Hardy space of the bidisc, you could look at the pair of operators TZ1 plus TZ2. So these are Toeplitz operators. Now, of course, that is of the form A plus B comma AB, with commuting operators TZ1 and TZ2. But if we restrict it to the subspace of symmetric functions, that's a closed subspace, that's Hilbert space in its own right. And if we restrict this pair, it still clearly acts, it's clearly the symmetric subspace of H2 is invariant under these two operators. So that's a well-defined commuting pair of operators. So yeah, so this really should say sim, shouldn't it? But it's pretty easy to show that it can't have a square root that commutes with these operators, because it would have to be like a square root of Z1 minus Z2 squared, but in preserving the symmetric functions, and so it's a small calculation that can't happen. So this is I think a more significant example to show that not all gamma contractions are simply symmetrizations of commuting pairs of operators. So I've introduced the notion of a gamma contraction. So it's a pair of commuting operators on a Hilbert space, for which this set gamma, the symmetrized bidisc, is a spectral set. And that means that for every polynomial g in two variables, the norm of g applied to this pair is less than or equal to the supremum of the modulus of g on gamma. And now I want to develop some operator theory for gamma contractions, which will be somewhat analogous to familiar operator theory for a single contraction. And so the first thing we need is a characterization. Of gamma contractions. And that's the following. If you have it for any commuting pair SP, of operators on Hilbert space. SP is a gamma contraction. So this is going to be the analog of 1 minus t star t is greater than or equal to 0. So that's just a single kind of polynomial inequality. But here we need a one-parameter family of them. And it's the following. For all alpha in the disk, 2 minus alpha s star 2 minus alpha s minus 2 alpha p minus s star 2 alpha p minus s is greater than or equal to 0. So this is one implication here is rather simple. So necessity. So remember we've got these functions phi sub alpha, and phi sub alpha. So let's observe this quantity here. Let me call that left-hand side, being the left-hand side of this inequality. So the left-hand side there, you can write it as 2 minus alpha s star 1 minus phi alpha s comma p star phi alpha s comma p times 2 minus alpha s. And you can do that all right because since mod alpha is less than 1 and the norm of s, let's see, have I assumed that? Yeah, right. So if we're assuming, what am I trying to prove? I'm trying to prove necessity. So I start off with s comma p as a gamma contraction, and from that it follows that the norm of s is less than or equal to 2 because you can apply the coordinate function, the first coordinate function, to s comma p in the definition of a gamma contraction, and you will deduce that the norm of s is less than or equal to 2. That being the case, for any alpha in the open disk, 2 minus alpha capital S is invertible. And therefore, I can talk about phi sub alpha of capital S capital P. It's a well-defined operator. And therefore, this way of writing it is legitimate. I can pull this operator out at the front and this one out at the back, and I get 1 minus phi alpha s comma p star phi alpha s comma p. Now, phi alpha is analytic for mod alpha less than 1. It's analytic in the neighborhood of gamma, and it's bounded by 1 on gamma. So less than equal to 1 on gamma, and that's for alpha in the open disk. If alpha has modulus exactly 1, then that's not quite true because we saw that there's a singularity at a single point in gamma, so that wouldn't be true. But for alpha modulus strictly less than 1, this is true. And in the definition of a gamma contraction, so S comma P is a gamma contraction if whenever you apply a polynomial that's bounded by 1 to the pair S comma P, you get a contraction. Now, phi sub alpha isn't a polynomial, but it's analytic in the neighborhood of gamma, and gamma is polynomially convex, so by the Jakob-A theorem, it can be uniformly approximated by polynomials. And so you conclude that phi sub alpha of S comma P is less than or equal to 1. Because S comma P is a gamma contraction. And so all this thing up here is positive, and so this is positive. So that proves the simpler implication, that proves necessity. I don't have time to show you the other one. For sufficiency, that's a rather long proof. So I won't really be able to go through that. But I want to rather show you the notions like gamma unitaries, gamma isometries, and gamma unitary dilations, and things like that. So I ask you to believe that sufficiency also holds here. And so we have this rather useful characterization of gamma contractions. There is actually a sketch of sufficiency on my slides, which are, I believe, already on the web. Anyone know whether that's true? Anyway, I think they're intended to be on the laboratory's web page. So let me talk about gamma unitaries. There's a natural notion of a gamma unitary. So it's a special kind of gamma contraction. So here's a definition. Let SP be a commuting pair of operators. Then SP is a gamma contraction. It's rather a gamma unitary. Now, what would a natural notion be for a gamma unitary? Well, think back to a definition of a unitary. One way you could define it is to say that it's a normal operator whose spectrum is contained in the unit circle, in the distinguished boundary of the disk. So that would say the natural S and P are normal. So the analog would be, and the Taylor spectrum of S comma P is contained in the distinguished boundary of gamma. So that might be one natural definition, but there are others that you could propose. So one would be that it could just be a symmetrization of a pair of unitaries. There exist commuting unitaries. So say this is on Hilbert space H, this is on the same Hilbert space, such that S is U1 plus U2 and P is U1 times U2. That would be a natural thing you could try as well. And then, of course, the most usual definition of a unitary is just an operator U such that U star U is equal to, the identity is equal to U times U star. So there should be some analog of that as well. And what we get is P star P equals the identity equals PP star. P star S is equal to P star And I think we need to assume norm of S is less than or equal to 2, yes. So those are 3 possible definitions you might give of what you mean by gamma unitary. And fortunately, they're all the same. So that reinforces the belief that this is a good definition. So that's a gamma unitary.
Looks very strange, P star S times equal P star, because it's not full.
Sorry, yeah, thank you. S star.
S. Yes.
Yeah.
Change the sum.
Yeah.
Sorry, is it possible to give a definition of gamma unitary contraction in terms of this estimate of the left-hand side?
Yes.
So
If you just expand this out, you'll well, we could do it. Let's take alpha to be in the unit circle to make it a bit easier. So what do we get? We get 4 minus 4 alpha s minus 4. I'm not doing very well, am I? 2 alpha s minus 2 alpha s star plus
Alpha bar.
mod alpha bar s star plus mod alpha squared s star s minus 4 mod alpha. Well, I said mod alpha was going to be 1, so let's just stick with that. So we would get 4 p star p minus 2 alpha p star s, 2 alpha bar p star s minus 2 alpha s star p minus s star s plus s star s. And now if we have these relations here, p star p is 1, so this one can go out with this one. Then I think everything just collapses, doesn't it? This plus s star s minus s star s, so those two go out. And then if I've done it right, yeah, this cancels with this and this cancels with this, and so it just evaporates into thin air. If I want alpha this.
we will just have 0 on the right-hand side, right?
Yeah, yeah. So what that shows is that this entire pencil vanishes for alpha in the unit disk, on the unit circle, in the case of a gamma unitary. Yeah. And now here's a theorem. Every gamma contraction S comma P has a gamma unitary dilation. So let me say a bit more precisely what I mean by that. So you can imagine you're going to have, you want, so S comma P, this is on a Hilbert space H. And so to talk about a dilation, you want a larger space K, Hilbert space K, and you want a gamma unitary on that larger Hilbert space. Such that, well, two ways of thinking of it. Let me write it down. So there exists a Hilbert space K containing H and a gamma unitary. Let me call it S tilde P tilde on K, such that so S tilde can be written like this, and similarly for P tilde for a suitable orthogonal decomposition of K. Now, you could start off by saying, well, P is a contraction, so we know it has a unitary dilation on some K, so we can get this one from known theory. And then S is an operator of norm less than or equal to 2 that commutes with P, and so the commutant lifting theorem says that there is an S tilde on K, so we take this to be the minimal unitary, take P tilde to be the minimal unitary dilation of P. Then the commutant lifting theorem will give you an S tilde which lifts to K and commutes with P tilde. But if you just use the commutant lifting theorem, the S tilde that you get by that, there's no earthly reason to think it's going that S tilde comma P tilde will be a gamma contraction, much less a gamma unitary. So it doesn't just follow from the existence of contractive intertwining dilations. But of course we're assuming much more about S comma P than that S commutes with P. We're assuming it's a gamma contraction. We're assuming this holds for all alpha in the open disk. And so you've got much more to play with. And in fact, we did construct a gamma unitary dilation in this form. So the main step in the proof was to show that if gamma is a spectral set for a commuting pair of operators, which is of course the definition of a gamma contraction, then actually it's a complete spectral set. So what that means is, in the definition of gamma contraction here, this is for all scalar polynomials G. That's how it was initially defined. But it turns out that a much stronger statement is true, and that is for all matricial polynomials. The same relation holds. And when you have a complete spectral set, then there are a whole lot of powerful star algebra techniques that you can invoke. The Alverson extension theorem and Steinspring's representation theorem and so on. And that's what we used to construct this S tilde and P tilde. More recently, some Indian mathematicians found a much more concrete proof of the existence of gamma unitary dilations. And that's possibly a superior way of doing it, really, because it's a bit unpleasant to have to use those abstract theorems that you can't actually get your hands on the objects. But anyway, that's how we did it. I think those Indians did have to use this fact. Did have to use the fact that we proved that being a spectral set implies being a complete spectral set. Well, in order to develop the functional model, we need analogues of various different notions from the theory of contractions. And so one of them is the notion of a completely non-unitary gamma contraction. So I remind you that a contraction T is completely non-unitary if it has no non-trivial proper unitary restriction. And so we can do something similar for gamma contractions. And then there was a simple observation that if you have a contraction T, then you can express it as the orthogonal direct sum of a unitary and a completely non-unitary contraction. And the analogous statement is true here. Every gamma contraction is the orthogonal direct sum of a gamma unitary and now what's the analog of completely non-unitary contraction? Well, it's a gamma contraction. Let me call it S1P1 such that P1 is completely non-unitary in the earlier sense. So P is a contraction, and it just has to be completely non-unitary. So there's something a bit non-trivial here. So suppose you've got your S comma P as a gamma contraction, then of course you can P is a contraction, so you can do the ordinary construction. So P is going to be, let's say, P naught orthogonal direct sum P1 on H naught direct sum H1, where P naught is unitary and P1 is completely non-unitary by the theory of contractions. Now, what is not immediately obvious, but is nevertheless true, is that these reducing subspaces H0 and H1 for P also reduce S. And therefore, when you just restrict S and P to these two spaces, these two reducing subspaces, H0 and H1, you do indeed get a gamma unitary and a completely a gamma contraction in which P1 is completely non-unitary. So that's a small calculation that shows that. So it's not completely trivial. Another important notion that we want to generalize is the notion of an isometry. Gamma isometries. So how should we generalize the notion of an isometry to the gamma contractions. Well, we have the definition of a gamma unitary here. So let's say S comma P, as usual, is a commuting pair of operators on the Hilbert space. Let's say it's a gamma isometry of what? Well, one possibility is that it's it just has a unitary extension. S comma P has a gamma unitary extension. So say S comma P is on H. What do I mean by a gamma unitary extension? I just mean that you can embed H in a bigger Hilbert space. So H is contained in K. And you can find a gamma unitary on K for which H is an invariant subspace, meaning it's an invariant subspace for both S and P. And this, for both, well, I haven't said that very well, have I? So there exists a Hilbert space K, H and K, and a gamma unitary S tilde P tilde on K, such that S tilde restricted to H is equal to S, and P tilde restricted to H is P, meaning of course that H has to be invariant under S tilde and P tilde. So that would be a natural definition for having a gamma unitary extension. Clearly, the analogous statement for a single operator, T, if you have an operator T which has a unitary extension, then then T must be an isometry. It's a restriction of the unitary to an invariant subspace. So it's an isometry. So let's take that to be the definition, and then there's a small theorem that says that you can express it in the following ways. S comma P is a gamma isometry if and only if P is an isometry, so P star P is the identity, P star S equals S star, and norm S is less than or equal to 2. So that's rather like the definition, like the criterion for a gamma unitary, except that we've got P star P equals the identity, we don't have P star equals the identity. So P is an isometry, not necessarily unitary. And another equivalent condition, that's basically the little computation that Raman was proposing, 2 omega S 2 minus omega S star 2 minus omega S minus 2 omega P minus S star 2 omega P minus S is greater than or equal to 0 for all omega in the unit circle.
Equals 0.
Sorry?
Equals 0.
No, greater than or equal to, I think, in this case. It's an isometry, it's not... there's going to be... Oh, you may be right there. Yes. Well, a small detail there that needs to be sorted out. Now, in the case of isometries, there's a decomposition. So basically, there are only two sorts of isometries. There are unitaries and there are shifts. And that's the content of the world decomposition.
Sorry, Nicholas, it's still not clear because we have two conditions which are looks very close. So in the upper board we have an inequality. Left hand side is positive. And
Yeah.
with the last theorem we have the same inequality. What is the difference?
Yeah, you're right, aren't you? Yeah. Well, maybe we should delete that. I think this is. I mean, there is clearly something to be thought about there. Maybe it should be 0. But I'd rather not assert that. Let's just ignore that. I think we can get by without it. We have a perfectly good definition of an isometry, and it.
With the quality, it was okay, I think.
Yeah, it probably was, but I won't risk it.
You don't use the property that P star equals 1.
That's right. Yeah. You're probably right, both of you. But I think we can manage without anyway. So let's talk about the world decomposition. So if you have an isometry, so if T is an isometry, so T star T is equal to the identity, then there's a rather simple theorem that says that T is the orthogonal direct sum of a unitary and a shift. A shift of some multiplicity. And we can make the obvious modification to this statement. So if S comma P is a gamma isometry, then S comma P is the orthogonal direct sum of what? Well, a gamma unitary, clearly, is one of them. But what's the analog of a shift? Well, that's what I call a pure gamma isometry. And all that means, a pure gamma isometry, is a gamma isometry for which P is a pure isometry. In other words, a shift. So SP is a pure gamma isometry. If it's a gamma isometry, and P is a pure contraction, that means, as we know, that means that the powers of the adjoint tend strongly to 0, and that for isometries is the same as being a shift. So we have in place now almost all the ingredients that we need to generalize the Nodge-Foyash model to gamma contractions. There's just one major item left, and that is the notion of a model gamma isometry. So let me introduce those. So let E be a separable Hilbert space. And let A be a bounded linear operator on E. Then I can define, so let's see, consider the following pair of operators. So the Toeplitz operator, this is going to be on H2 with values in E. A plus A star Z. So this is the Toeplitz operator, T sub Z. So in other words, that's just the forward shift on H2. And this is the Toeplitz operator with the symbol A plus A star Z on H2. And they're analytic Toeplitz operators. They're both just multiplication operators. And so if we call this S and we call this P, then certainly P star P, so P is the forward shift, so it's the identity. And let's look at P star S. So that's T Z star T A plus A star Z. So T Z star is just T sub Z bar, and because this is an analytic Toeplitz operator, the Z bar just comes in here, so we just get T Z bar A plus A star. So that's T of A plus A star Z star, which is S star. So that's close to being a gamma isometry. All we need to make sure that it is a gamma isometry is that the norm of S should be less than or equal to 2. So the norm of S is the norm of T sub A plus A star Z. But the norm of a Toeplitz operator is just given by the supremum on the unit circle of the norm of the symbol A plus A star e to the I theta. So that's this. If we multiply in here by e to the minus I theta over 2, we would get so sup over theta of the norm of twice the real part of A e to the minus I theta over 2. And that is equal to twice the numerical radius of A. And so we conclude that this operator, Ta plus A star, this pair of operators, is a gamma isometry if and only if the numerical radius of A is less than or equal to 1. So that was easy. And in fact, this gives you all pure gamma isometries. Every pure gamma isometry is unitarily equivalent to one of these. So that's going to be our model pure gamma isometry. And so when we come to developing the analog of the Nodge-Foyos model, one of the ingredients that you have there is are these model operators, model isometries, model gamma isometries, model pure isometries. And so now we have in place all the ingredients we need. And so in tomorrow's lecture, I want to describe how the Indian school, so notably Tirtha Bhattacharya, Saurav Pal and Jadeb Sarkar, they combined all these things and derived, I think, a very compelling functional model for gamma contractions.
Thank you.